Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks everybody for coming. I'd like to introduce you to Dr. Jae Young Park from EMC Squared Corporation. Before we get going, I'd like to thank Dr. Park for taking the time to put these slides together. He spent a lot of time doing it. I'd like to thank our former fellow employee, John Costello, for introducing me to the concept of Polywell Fusion and making me spend long hours researching it, which has all been to my benefit. And I'd like to thank Amy Draves and MSR for hosting the talk. You may also want to refer to the 2006 Google Tech Talk featuring Dr. Robert Bussard for more background. Microsoft adds value to electricity, and we want everyone to have a cheap and plentiful supply. But the cost can be very high in terms of environmental damage, emissions, resource consumption, and access. If you're a liberal and hate global warming and want clean power, if you're conservative and want to make electricity cheap and make more money off of it, if you're libertarian and want to see something like a Galt machine finally arrive, or if you're somewhat disgusted by primitive practice of combusting stuff to make electricity, Dr. Park has something for you. And for the cost of a handful of McMansions, we can make real progress in this area. So, Dr. Park?
Thank you. Thank you. So let's see, I think I want to go back to the first slide. So thank you. Thanks, John and Amy, for inviting and arranging this trip. I'm excited to be here, and I hope this will be a good talk. I was told that my timing was pretty good, impeccable, because I think the whole city of Seattle needs a few more days to recover from the game on Sunday. So congratulations for that. And I'm excited in about 10 days for the Super Bowl. So let me start with the last page first. You probably heard about these courses on fusion before. Fusion is the ultimate energy source. And it is 20 years away, and it will always be. My goal today is to share that there's a hope that we can have fusion power the world in not so distant future. So this is a slide I first used when I was giving a talk at UCLA. And well, it's LA, so everybody gets their fame for 15 minutes of fame having a mugshot on TV. So these are the gentlemen. This slide reminds me of how privileged I am to follow the footsteps of these gentlemen. Their brilliance and their ideas, what makes the Polywell an interesting opportunity to study fusion. So as it happens, my talk today will be more focused on these two gentlemen here, who has direct contribution to a lot of Polywell physics. Professor Harold Grad is from NYU, and Dr. Bussard is the founder of EMC2. So here is the outline of the talk. The first, I'll start with a fusion, primer on fusion, which will then talk about those two courses here a little bit, why that makes sense. And then follow the story about Polywell Fusion, and quick glimpse into the minds of these gentlemen. After that, I'll describe what we learned at EMC2 in the past couple of years. And this was supported by US Navy, so we're very grateful for that, their support. And also, I'd like to emphasize this was a teamwork, and I'm very excited to present our team's result here. So thanks for those, and that's why I'm here today. And then I'll wrap it up the talk about the future, the vision that we have that we can hopefully, in a not so distant future, will power the world with the fusion energy. So to some of you who are not familiar with the fusion and doesn't have a smartphone next to you, this is a one-page introduction of the fusion. Fusion generates a usable power from merging of the two lightweight atoms, such as deuterium and tritium, and release a large amount of energy based on Einstein's equation, E equals mc squared. It's an incredible source of energy. If you look at here, by fusing just 2 grams of deuterium and 3 grams of tritium, you can generate approximately 1.7 terajoules of energy. That's equivalent to burning about 270 barrels of oil. So it is an impressive source of energy. And there are reasons for that why fusion is called the ultimate energy source. There's abundant supply of low-cost fuel, no danger of the nuclear fission type of accident, no greenhouse gas emissions, no or minimal danger for non-nuclear proliferation. And also one of the benefits of fusion is there's no radioactive fuel residues. So you generate some nuclear reactive waste if you use a DT particulate fuel, but those are low-level waste, not that much different from hospital type of waste, and they don't live long. So you don't have to worry about long-term waste depository. So this is a good part about fusion. So what's the hard about it? Well, just like everything else, trying to do something great requires hard work, and fusion is no exception for that. So there's a graph here you can think about as a probability of fusion happening. And first thing you'll notice in x-axis, by the way, this is a conversion factor. So 10 kb here is about 100 million degree. So you do need to keep the fusion hot, and this has something to do with overcoming strong Coulomb forces. That's not just one. If you look at this y-axis carefully, the number there is about 10 to the minus 27, 28 square meter. What that is, fusion being a nuclear forces, it requires two nuclei come together very, very close, about 0.1 to 1 times 10 to the minus 14 meter. Everybody heard about the nanotechnology. 1 nanometer is about 10 to the 9 meters. So the scale that is relevant for fusion is about 100,000 times to 1,000,000 times smaller than nanotechnology. So what that results in is typically in Polywell or more of the conventional magnetic fusion reactor, a single nucleus has to travel about 10,000 kilometers to generate one fusion event. That's how unlikely the fusion happens in nature. So that's why every time you hear about the fusion, one of the words you hear is called confinement. You have to design a very clever container to contain this 100 million degree fuel very efficiently. So they'll go through fusion collision before they escape to the wall. So that's a pretty tough odds. And in fact, these odds were well known since 1940s in physics community, and that didn't stop the people to pursuing fusion. In fact, from what I gathered these days talking to people, they were actually more optimistic about the chance of making fusion in 1950s and 60s. And here's the summary of their effort. Obviously, it's a tough problem, so it takes some time to get started it. But once they started it, they were making a tremendous progress about 30-year span. And culminating the work here done in joint European tokamak, which is in England, that produced approximately 16 megawatt of fusion power with an input of 24 megawatt. Here in US, there is a Princeton work in 1995 which produced about 12 megawatt of the fusion power, and that's the data point here. And I also like briefly mention there's another approach for fusion uses a laser, and they were also making a great deal of progress at the same period. So it is a sort of the general agreement among the fusion scientists and most of the scientists that fusion is going to happen sooner or later. The real question is, how fast can you make it work? And if you make it work, whether it'll be economical and practical. So before I talk some more about it, please do.
What is the split of the input power? Where is it going?
I will talk to you a little bit more about that, but generally the next machine for ITER will be about 100 megawatts, like 50 megawatts in, about 500 megawatts out.
Where what is that energy being used for? Is it containment or
Heating.
Fuel? It's mostly heat, not.
It's a heating, and containment is more like the insulation.
Okay.
So you heat it, you lose the heat fast, it'll never get hot. So you have to contain it, provide a good insulation. So it's all in the heating side of it, and that handles both confinement, because every particle you lose, they take the energy away from it. Yeah, I forgot mentioning, if you have a question, feel free to ask, and also I'll have some time to answer it at the end of the talk as well. So this is a slide I put it up all year. I'm excited to be here at Microsoft, and partly because it's been tremendous help for the fusion community to have a high-performance computing. And this is an example about structures and details of the fusion plasma you can now simulate with the help of the supercomputer. Well, it's a little slow, turns out to be. To do it right, it takes about 2 days of simulation to simulate about a millisecond of the real life. But nonetheless, it's a good place to start. So if you can make a computer work faster and better, we're all ears. So thank you. So I told you a little bit about it's getting close to the fusion. In fact, this graphs here is an amazing testament of how much we made progress in understanding plasma for fusion. X-axis here is experimental data, Y-axis here is a theory, the modeling. And the agreements are pretty good. And based on this agreement, we're able to design a machine called ITER. ITER is not an acronym, it's actually the Latin word called away, that will scheduled to produce more fusion power output than its input power. And that began at about 1984-5, and it's between Russia, I think at the time it's the USSR, and America agreed to build the ITER. And you can see the pictures of the gentleman who signed the agreement. So this is 2015. So that's almost 30 years ago. So it has been 30 years today. So ITER is finally being built in France, and it's actually making a pretty good steady progress. If you look at the schematics, scale schematics of ITER, I don't know whether you can see, you have to look really hard, but you can see a 6 feet tall person. And you can this picture give you a sense of size, how big this device is. I personally believe ITER would be a great scientific machine. I'm so excited about it. I would like to see it working. On the other hand, here's a hard fact. It's going to be big. It's going to be a very complex machine. And unfortunately, it's taking longer and longer and more expensive to build this one. So it's probably 2030 is what I heard the latest number. It may be even more longer if we have to wait it. There's another case. I mentioned briefly about the laser approach in fusion. This is another flagship fusion device. This one actually has been built and operational at Livermore National Laboratory in California. The idea behind it is called laser-driven inertial fusion, that small pellet-sized fuels are compressed, heated, and ignited by lasers to produce bursts of fusion energy. NIPS uses 192 power laser, and the facility is about 3 football field size. So you kind of wonder, it's starting to make sense. Yes, we're making a lot of progress, but it looks like we're making bigger and bigger and more complex. And as such, the reality of fusion power looks like further and further away rather than getting closer. So the consequence of that is we're in the world that everybody wants to use more electricity or more energy. There's a growing world economy in China, India, Africa, and everywhere. There's a need to address those energy consumption. So for the people or for the world, these are the sort of the electricity market trend. And they're counting on coal, natural gas, and nuclear power to make up those needs. And about 75%, according to the projection by US Energy Information Agency, by 2040, 75% of the electricity power will come from those three sources. If you look hard enough, there's a section for the solar and wind. It's there. They're growing about 10% a year clear. Despite those rapid growth, they still have technology problem to solve. And this prediction take that into account. So you can kind of see that it'll be great. I was actually talking to John this morning. It'll be great personally if there's a way we can generate electricity without burning coal in some way. That'll be great. I mean, you may have to burn coal, but less you burn it, you're probably better off. So fusion can help with that if you can do it sooner rather than later. So here's a story of Polywell Fusion, and that's why I'm here. But in fact, this is a question that started EMC too. Big and complex machines are expensive. They take a long time to build. If you're smart and young and curious scientists at work, you sometimes have to throw the question like this and think about it. And that's how we started EMC2. So the idea starts from this concept called electrostatic fusion. It doesn't use magnetic field. The basic premise of the electrostatic fusion is you form electrostatic well. You form the well, potential well. Ions here, which is essential for making fusion works, gets contained here, gain the energy by the time they go here, circulate it, move up, go back here, go back out, and in the middle, they generate the fusion event. By utilizing electric field, they are guaranteed to be quite efficient in confining and accelerate those ions. And that's been one of the reasons these concepts are very successful making fusion event. And the well-known version of this concept is called Farnsworth fusor or Hirsch-Farnsworth fusor. You can kind of imagine Dr. Bussard, who started EMC2, used to work with Dr. Hirsch at US Atomic Agency. Dr. Hirsch did his thesis, postdoc work with Dr. Farnsworth, Philip Farnsworth back in 1960s. So in a way, they knew this, and this was a good place to start it. One of the nice things about this, and I personally built one of those myself, is now the 6-foot man becomes bigger compared to the machine. And it's a pretty neat little device. You can make lots of neutrons and fusions in the system. However, despite all the best effort, it looks like producing net power in an electrostatic will be very challenging. And that's because electric fields are good at attracting or confining one species at the expense of pushing out the other species. So for the electrostatic concept relevant to Polywell, which is a potential well, is great for confining iron, is really poor confining electrons. So the electrons just flies away, hit some of these grids and get lost. So the power gain efficiency is about 1 parts per million or 1 parts per 100,000. It's very small. So about 1985, a young scientist, I guess back then he was young, Dr. Bussard, and came up with the idea that, well, I'm going to insulate this grid where the electrons get hit, lost, by flowing the current in the coil. So you can actually see it here. And that helps the electron to avoid hitting this coil. So there's a concept called magnetic insulation. Turns out what is really original about his idea is not the idea of insulating it, but what type of magnetic field he chose to use to do the job. And that's the story of Polywell. Polywell is a combination of polyhedral coil that is used to confine electrons, and potential well that is used to confine ions and provide a heating of the ions. And that is in 1985. And it's a little difficult images, and if you stare at it long enough, you'll make some sense out of it. These are sort of the three-dimensional pictures of how the magnetic field look alike in Polywell device. I'll just leave it at here, and then I heard that it's going to be available online or the public forum, so you can stare at it a little more. So after spending some time, EMC started working on it, building experiment in around early 1990s. And turns out, forming a potential well in a Polywell device by electron beam injection wasn't too difficult. So we have some early success by about 1995. The potential well, you see it here, is about 7 point, I believe about 2 kilovolts. Go ahead.
In the picture on the left, it looks like there's streaming paths on the vertical and horizontal axis. Is that an issue? Or?
Oh, you mean this one here?
Yeah.
That is an issue. I'll talk to you a little bit. So that is an issue because that's where your electron is going to leak out and disappear.
Why is confining the electron so important?
Because in order to create a potential well, you have to inject the electrons, and electrons gives up the energy to create an electric field. So if you lose the electron, you're not going to form a potential well.
I thought the potential well was created by the current flowing around the rings.
No, those are the magnetic field.
Okay, got it. I see.
So current flowing here, currents going into that create a magnetic field shaped like that. And you shoot the electron into these corners to create a potential well. More electron you confine it, deeper this well becomes.
On the last diagram, you have label at low plasma, not that, the slide later. Keep going, there.
Yes.
At low plasma density, does that mean refer to the density of the injected ions, or are you referring to the electron density?
Density of injected ions, density of the plasma that is to be accelerated.
By low, do you mean that it's many fewer ions than there are electrons?
You don't need a big difference. You need about, so what ended up being is approximately you need about 10 to the 7 or 10 to the 8 per cc difference between electrons and ion concentration to create a well like this. Generally what they see is, this was done, I used to have a slide here, but done at about 10 to the 9 particle per cc as they try to raise up the density higher to make a more fusion power output. Well disappears. And that was attributed to electrons, even though they're putting it about few amps, they don't last too long. They disappear, comes in here, as he asked me, along these lines, they get lost within somewhere between 30 to about 100 nanoseconds in this type of device, meaning that they just disappear so fast that you're consuming so much power to create a very weak potential well. And as soon as you start trying to accelerate the ion, the well stops collapsing it because you're not having enough electrons in the system. So what we was found to be is somehow in order to make a Polywell work, you need to have ability to contain these high energy electrons. Not just electron, but high energy electron for very efficiently and long time. So that was the challenges EMC took on it. Over the next 20 years, we have built several devices, WB1 through WB8. I guess 2 is here, 4 is there, 6, 5, and 7, and 8. I'll show you the scale about 8, what it looks like. It's about this big. So we try really hard confining high energy electrons in this system. And reality is, none of these devices, all the way up to 8, succeeded confining high energy electrons. So you kind of wonder, well, the idea was great, but something's not clicking here. Either we're missing it or we're doing something wrong. So it gives you time to think, what are we missing? So we're going to take a second look into the Polywell and look at it differently. Not just isolating those grids, but what is really going on and what you need to do. So it's called diamagnetism in plasma. What makes the Polywell interesting is this concept called diamagnetism. This happens in plasma because in plasma, it's not a neutral matter. Electrons and ions are now free to move. When they move, they generate the current. When they generate the current, the direction of their current is try to cancel out the magnetic field that was imposed onto them. So that's the word diamagnetism comes about. More plasma you have, this diamagnetic effect becomes stronger and stronger until you can cancel out all your magnetic field in the system. So what we were looking at is, with increasing plasma pressure, the Polywell dynamics will change dramatically due to this effect. And in a way, this is somewhat similar to the magnetic gravitation in a superconducting material called Meissner effect, and there's the cartoon and pictures of that. You can see the gravitation on it. So that's sort of the effect we're looking at it. Here I'm going to define a parameter called beta, which will be used extensively throughout the rest of the talk. It's the ratio between plasma pressure and magnetic pressure. So more plasma for given magnetic pressure, you have a higher beta. And that will be an efficient use of power, because it turns out the fusion power output goes up as a beta square and a volume. So if you want to make a small reactor, you have to increase the beta. If you have a small beta, you have to make up for that by making the device larger. That's the direction. And here's the pictures about it. I don't know whether you can see the line. If you look closely, there's a white lines going through. That's the magnetic field. The colors are plasma. When there's not enough plasma, even though they try to cancel out the magnetic field, it's not strong enough. So you can see magnetic field penetrate into the plasma. When you have sufficiently high plasma in the system, there's no magnetic field. All the fields get pushed out. So in the big region here, you have a field-free and plasma region, and the magnetic field get pushed around at the edges of the boundary. Okay, if you have a hard time understanding this, that's okay. We'll have some more slides to do it. Before I want to do that, I want to just talk a little bit about short history. This will help you understand the importance of the diamagnetism in Polywell. So this is a snapshot of the US fusion program in 1958. And the stories of the next few slides are from the book from Project Sherwood, written by Marshall Bishop. And Bishop was the program manager for the US fusion program in 1950s. It's a very good book. So the story begins with Edward Teller in 1954. Teller is a pioneer in both fusion and fission. And he's a very brilliant man. So when he heard about it, some of the younger scientists at the time were working on fusion to be a power reactor. He threw a questions. He said, well, you guys are missing something here, and it's called plasma stability. In his view, containing the plasma with a magnetic field are kind of analogous to trying to contain the jello with a rubber band. It's kind of, okay, good. What it means is jellos or plasma always like to move outward. They like to escape, they like to move outward. Magnetic field has a similar property as a rubber band. They always like to snap back into the shortest distance possible. They don't like to be stretched. They like to be snapped back. So I'm going to look at this called unstable picture here. So plasmas here like to go out. Magnetic field is already stretched. If you think about it, they would rather go in to make it themselves shorter. So what happens is when the opportunity arises, plasma will move out, magnetic field will snap in. They'll change the position. So they name it as an interchange instability. It's sort of analogous of the Rayleigh-Taylor, more well-known fluid instability called Rayleigh-Taylor instability. So they find out this configuration will be inherently unstable. Opposite, if you have a magnetic field shape looks like that, plasma would like to escape, but magnetic field say, well, that's okay, because I can make it myself shorter that way. So that boundary remains intact, and that is considered stable configuration. In some of the devices, you have both region as unstable region and a stable region. And this is sort of modern day cartoon about what it looks like in a tokamak. If you look at carefully out here, this region has unstable configuration. Therefore, you see lots of instability being developed that area, while the inside, which is stable, is much more quiet. So that was the point he made it. back in 1954. Turns out his intuition is absolutely correct. And almost all magnetic confinement system suffers the instability, as he predicted. So what happened was back in late 50s, majority of effort in fusion went in to stabilize the plasma against these type of instability. And they succeeded to a large degree. And that's why you saw those tremendous progress in an earlier slide. However, it left one lasting legacy, that higher the plasma beta, there's always maximum beta you can have in your configuration. Turns out that maximum beta you can have to stabilize the plasma is not very high for most systems. So ITER turns out to be that number is about 0.03. I remind you, the fusion power output goes as beta square. And that's one of the reasons the ITER is so big. For that confinement, there's an interesting quotation I got from that book. Is Herbert Yoke is the first laboratory director at Lawrence Livermore National Laboratory. He learned about the effort back then goes on in Princeton University, Princeton Plasma Physics Lab, and called the device called Stellarator. He said, well, because of all the bendings and funny shape, he think that there would be a significant limitation on beta. So reduce the power output, because you can't really have a high beta. So for given size, your output has to go down. That he think it'll never be of economic interest. So he directed one of the young scientists named Dick Porse, to work on so-called magnetic mirror fusion program at Livermore, which later turned out to be also unstable at high beta as well. Well, if you look at it, laser fusion still struggles with it. It's because of the instability. In their case, it's more the traditional Rayleigh-Taylor type hydrodynamic instability. So, summary is, fusion devices become bigger and bigger because they have to battle this instability. So if you can control the plasma stability, you have a chance now to make a fusion device smaller and more economically attractive. So that's the story about Cusp. Cusp came to existence. Let me just go back here quickly. I forgot mentioning it. There's a Cusp geometry starts at about 1954 and 55 at NYU. Cusp started it because it is an answer by a gentleman named Jim Tuck at Los Alamos. Hey, I'm going to create a system where the coils are positive in and out and in, change the polarity, create a magnetic field. Looks like the picket fence along the garden, British garden. And in the plasma, everywhere you look at it, you see a good curvature. Therefore, it turned out to be absolutely stable against interchange instability. It's the first magnetic system to do so. So they thought, well, this is a good idea. Turns out when they run the experiment, the losses, as you pointed out, through this field line was super fast. So it was almost like, well, it looks stable, but there was hardly any plasma in the system. And that was a problem. Until somebody came into and thinking, well, let me think about this. And that's the work by Harold Grad and his team at NYU. They took a rather drastic approach. In their view, plasma diamagnetism will do something. So if you happen to have a very high pressure plasma in the cusp, they'll then push out the magnetic field, and you have a giant area where there's no magnetic field in the system. You'll have, because magnetic field never disappears in nature, you will push them and you will pile them out in this boundary. It'll dramatically change those interface between plasma and magnetic field region. And when that happens, he estimated the confinement property of the cusp will be dramatically different, and it will be a lot better. So we run some numbers about contemporary numbers about 6 coil cusp system with a 7 Tesla and about a meter radius coil, and trying to contain 100 kilovolts. That's about 1 billion degrees if you converted it. If you're in low beta pressure in these cases, expected confinement time is about a microsecond. If you somehow Grad is correct, And if it's in the high beta regime, according to its prediction, it's about half a second. So we're looking at about 500,000 times difference. It's not like, well, as a physicist, that's very big. That's almost like a phase transition between ice and water. It's a completely different system. So I'm going to take a little pause and look at this one. So back in 1985, when Bussard started working on Polywell, he knew about Grad's prediction. He thought this would be important. So this is a quote out of one of his seminars. The enormous flux of electron at the center exhibit the diamagnetic effect. It excludes the magnetic field outward. This pushes back the magnetic field outward and contracts some of the holes where you see the particle may get lost. This is sort of the very graphical, kind of visual interpretation of the Grad's theory. And he named that as a WiffleBall. So Polywell is not just creating potential well, but it utilized this concept called WiffleBall. Because without forming a WiffleBall, you don't have a means to contain those high energy electrons efficiently. So what happened to the Grad? So after the Grad, his conjecture made a Cusp approach promising. And you saw that earlier for net power producing fusion reactor. As a result, there are significant experiments were conducted in the next 20 years on about 20 different devices, and about 200 papers were published. There are 2 excellent review articles by Spalding and Haynes. But most of the effort on Cusp stopped by 1980 because lack of progress. Cusp was a very difficult machine experimentally, as well as some of the experimental data cast a shadow to the Cusp confinement predictions. So why Polywell, not Cusp? So now you're kind of starting to wonder, when Bussard introduced electrostatic concept onto this Cusp, what he ended up doing is he's making 2 changes, making a significant changes, basically address 2 of the most challenging issues of the Cusp system, make the Polywell better. And here's a little cartoon. So this is the electrostatic idea, and that's the magnetic Cusp idea at high beta. So one of the reasons effort at Cusp stopped is there's not an easy way to heat the ion to the fusion temperature. Electrostatic, that's not a big deal. You use electrostatic potential well to do that. You inject the electron. If they get confined by magnetic Cusp, you will form a nice potential well that will accelerate the ion to the fusion temperature. Second part of the thing is there's a lot of debate for the next 20 years between 1958 to about 1980. There are a lot of debate about which of the loss rate in the Cusp is correct. Is it driven by electrons, driven by ion, or more of the hybrid by both? I think it's still unresolved problem by and large, but in Polywell, we bypassed the problem altogether because of the potential well, ions, where their boundary, they're already cold. They have to climb up the hill to cool down significantly. So if you lose them, it's not a big deal. In fact, cold ion loss at the Cusp boundary is actually smaller than the hot electron loss at the boundary, so it doesn't matter. All you have to do is count the electron losses, not to worry about the ion loss. And that is a very big simplification on the part of the Cusp system. So that's why Polywell is a very interesting concept, and that's what makes me excited about it. And it took a while for us to go through all those, but we're finally here to get that. So these are the experimental work at EMC2. So I'm going to start with some of the pictures here. That's the WB8 device we built. Oh, sorry. Okay, please.
So it seems like the appropriate measure for electron loss is something like cross-section through the holes as they shrink, like this, the cross-section of the holes as they shrink? Or what do you use? I mean, what's the, like, there's a cross-section for fusion, there's a cross-section for escape. Is there?
We'll get that one maybe at the end of the talk, because that's a little bit tricky. I'll be happy to answer that, but maybe at the end of the talk. So thanks. Any other questions?
When you say high energy electrons, what kind of energies?
So in our current set of experiment, we use about 7 kilovolts. In a fusion device, we're looking at about 50 to 100 kilovolts electron. And those has to be confined.
So they're relativistic.
Not quite. Electron, well, I guess about like 10%. So yes, but it's not heavily relativistic at all. It's a small modification. So thanks. Okay. So I think that's me. And this is a device we tested out, high beta Cusp confinement system. These are the pictures. We took it during the installation of this small device here. That's where the coils are. And you can see some of the diagnostic called flux loop to measure the diamagnetic effect. Because a WiffleBall or the Cusp confinement being a diamagnetic effect, we need to measure them, make sure that it's there. So this is an animation, so let me hope that this works. So this is experimental setup. And that's the device we have. And you can see some of the dimensions here. So we're very much interested in confining high energy electrons. So we had an electron beam gun coming from the top that puts out about 7 kilovolts of electron into the system. We use so-called plasma gun. Each one handles about 350 megawatt of power for a short period of time. We're injecting plasma, so we'll see from low beta to the high beta, back to the low beta transition, and we're going to monitor the electron confinement through the X-ray measurements. So that's the game plan on that one.
That's presumably the plasma gun is a pulse.
Yes, those are pulse for the time being. Eventually, it'll be held steady state as you move toward it. So you will do this once. And what's nice about this Polywell concept is if you do form high beta confinement state, you don't have to put out that much power to sustain it. Your power requirement to sustain goes down significantly. But for this test of experiment, we just did it post.
And for this scale of machine, the intuition would be that the most active region is that diamond where the field is being excluded. How large would that diamond be?
We're looking at about 10 centimeter in radius.
For the central area?
Yeah, for the central area, the whole area here.
So that's a relatively large area to have no field.
Yes. Yes.
And
that's what it requires. And we done some measurement to indicate it. That's what's happening.
And inside that area, what's the distribution of electrons? I would imagine that they would try to avoid each other, so it would actually be relatively hollow.
Not really. Keep in mind that, again, this case in particular, we didn't try to produce the electrostatic potential well. So the plasma is largely neutral. And this electron beam that was used is, let me just give you context. So we put 2 of them, that's about 700 megawatt of the power injecting neutral plasma. And I have about 3 amps, so 7 times 3 is about 20 kilowatts of electron beam. So you can easily see I need a lot more than that to start creating a deep potential well, accelerate the bulk ion in the system. So it wasn't designed to handle deep potential well on this one. These beams are used as a diagnostic goal to monitor whether you can have a good confinement on those high energy electrons. So you can read about this later. I'm just going to flash here. The game plan for that is we're going to start with a bulk plasma that was injected by this gun to form a high beta plasma in the center that will modify the Cusp magnetic field in such a way the confinement property of high energy electron will be changed. And we're going to monitor them using X-rays.
What is the temperature of the plasma in your system?
Thus, bulk plasma we expect to be about 10 electron volts. And the electron beams are 7 kilovolts, so they're very different. So they don't interact much at all.
10 electron volts.
Yes.
Yeah, so it's about
100,000
100,000
Kelvin. versus 7 kilovolts, which is a lot higher. So here's a little bit more pictures of it. These are the actual device we use to form arc injection. It's about have a center gap and about 2 millimeter gap. We use the polypropylene solid target, which is about 1/5 or 1/10 of the sarin wrap thickness. So we usually send one person, he laid out with the soft hands flatly, and we flow about 100,000 amps of current. And that generates 350 megawatt of peak power plasma injection for about a 7 microsecond. And by using 2 beams, I think I can do this. And it might be a little jumpy because we have to take the pictures on simultaneous shot. It's not done in a fast shot. So this is how the plasma, 2 plasmas come in, they merge, and they brighten it up. Let me play it one more time when it's done. You can see that plasma comes in, they form it. Because of what's limited it was a limited budget experiment, we didn't have that great a symmetry. But nonetheless, in the bulk volume, you do have a very high pressure plasma forms, and that seemed to be sufficient to actually dramatically change the confinement property of the electron. That's what we've seen experimentally.
So when you say what's the pressure in pascals would that be?
This case will be about 10 to 100 Pascal for this one. They're not that high.
So about a millibar?
Something like that, probably. I might have to check the numbers on that one.
How long do you keep the plasma?
Pardon?
How long the plasma stays?
Oh, I have a diagram. So if you wait, just so you know. So that's sort of the plan is that when you inject electrons do move around it. They do get lost at a low beta through those holes. When they form high beta, ideally these loss would be a lot smaller, so they'll stay more. And that concentration of high energy electron will be measured by X-ray diagnostic. Give you a perspective. These 7 kilovolt electron for this small device, they move very fast. It only takes 7 nanoseconds for them to move one end to the other. On average, at low beta, we expect them to last about 45 nanoseconds. Hardly no time, they just disappear. What we are hoping to see is by making a transition to high beta, we like to see them stay in the cusp approximately 400 times longer. So if you look at the X-ray signal, it's like no signal, mucho signal, and back to no signal when it disappears. That's what you want to see it. You have to see it so clearly with your naked eyes, basically. So that was a goal. So here's a movie. It does have a very interesting sound effect, but let's see.
8, 7, 6, 5, 4, 3, 2, 1.
We have some young scientists works there. I think that was his view of it. I'm going to turn it on again. So what it is, like we count them at about 0. We shoot those fast injectors. They make a very bright plasma. We keep the diagnostic going throughout the whole time and make sure that we see them, how the X-ray signal changes as a function of the time throughout the process. So I'm going to just show it one. And obviously safety is very important. And I was told that I can't really look at directly, so we put the mirror here, so you will see the reflected light from the mirror. That's what you see. It's not as spectacular as a result of it, but one of us thought that's safer that way. So nobody got hurt. Everybody's happy. So it was about 2013, late October, we finally make this thing work. It's called WiffleBall. And that was the pictures of the plasma with about 700 megawatt of injection power to start it and form high density, high pressure plasma in the middle. So this is one of the first data. I think that day we took 2 data, looks about the same. I decided to call it a day. Just because I was pretty excited about it. So these are the case when we have electron beam turns on here. At t equal about 40 microsecond, is a microsecond in the X domain. And we monitor it, there's really no X-ray. obviously there's confinement of the electrons are poor, and there's no plasma to make an X-ray with it. At t equals 0, we inject about 200. This blue here is about half of the power. It's about 250 for that channel. I think if you combine it, the other one is higher, so that's about 700 megawatt. You inject that. You can see them move into it. You can see the density shows up here. What you want to pay attention to is this delta B. That's the measure of the diamagnetic field at the location that we put those diagnostic. We see that it peaks out. Just shortly after it peaks out, you can start seeing the X-ray signal start rising up. And then and it rises gradually for a period of time. At some point, it crashes down. And we really like this signal, and I'll tell you why. First of all, we weren't really trying to sustain this high beta regime. So when we started it in a vacuum to a high beta, we expect it'll decay away. And you can see some of the line emission that plasma is getting cold, and you're starting to lose plasma. So high beta regime exists about 3 to about 5 microsecond period in this set of experiment. What you want to see is, initially, confinement of the electron is poor. So you want X-ray signal to go up gradually as the confinement get better. Because all of a sudden you turn off the switch, all of a sudden all the losses disappear, but there wasn't much electron at that point in time. So you're building up gradually. When you lose them, all of them has to go out all at once. You can't expect them to go out slowly because all of a sudden all the good confinement's gone. So now they have to disappear in about 45 nanoseconds. And that crash there is about the resolution of our instruments. That's about a microsecond. So you can see why this signal was so pretty. And you can see how big a jump you notice it. Later, we also noticed there's an interference from the impurity that is being melted into the system in those discharges. And we find out that's not something to worry about. So we're fairly confident that that's not the case. A few days later, we convene it and we continue to do experiments. So one of the things we do is we vary the power. So black here is 200 megawatts, 350, 450, and 700 megawatt. I mean, 200 megawatt is not bad. It's a significant power, but it hardly makes any dent at all in your X-ray signal. And even 350, there's not that much, so you might see a little blip there. It's only when you have sufficient power, you see dramatic change in your X-ray signal. Again, the shapes are more triangular shape rather than a square shape, which is what we expect to see. We've done that by keeping the power the constant. We then vary the magnetic fields. First of all, we want to make sure that this is a magnetic effect. At B equals 0, there's a black, and there's really no structure. Some of these related to impurity. And obviously, there's no diamagnetic signal, no magnetic field. There's no reason for the plasma to produce diamagnetic effect. When you have just about the right balance in red, you see giant signal, and that's when you see it. When you turn up this blue, which is a weak magnetic field, you have this case that plasma is overpowering the magnetic field. When the beta is bigger than 1, in general, you cannot expect to have a plasma confinement. So everything gets sloshed around it, and that's what you see as well. So this phenomena, you can only see it when there's a decent balance between electron and magnetic pressure from the plasma and a magnetic field. So that made us feel pretty good about it. This one day, we shoot 6 shots. So every time we send it, open the chamber up, send 2 people, take it out. There's one person with a good hands, manually that out. So it's not a very easy to control experiment. And you've seen that, like if you watch it, it's like sparks flowing. And it's somewhat of an uncontrolled experiment. These are the 6 consecutive shots we did it that day. And you can see that distinctive features are all there. And it all has that particular shapes. Later on, you have lots of variation, depends on how much metal you take it out. So, but those are much later time, and they don't have such a rapid crash or change in time. So which make us believe that, yes, this looks like the real, and that's what we are seeing. Just estimated how long a confinement time we're measuring it. One thing you don't want to do is you measure signal with a large number to the small number where you have a lot of errors. that will arbitrarily create a big numbers, especially if you divide by 0, that's not fun. What we did is we look at how fast this rises. And you can solve some of the equation, and that time is about twice as long as your confinement time. So we got about 2.5 microseconds. If you remember it, expected confinement time of these fast electron when there's not enough plasma pressure is about 45 nanoseconds. That's about 50 times more. That's why you see dramatic changes. You don't even have to measure it. Your eye just sees it. There's a big jump in X-ray signal. So, obviously, as much as we're excited about it, there are a lot to learn about it. And these are the physics issues we will hammer it out. We need to tackle this. We need to learn more about them if you make a progress in Polywell. So that's what we're going to be doing here. Nonetheless, this experiment was very satisfying, considering it took us a long time. It's particularly satisfying. The X-ray measurement clearly showed that you can enhance the electron confinement and high beta cusp, that WiffleBall effect. We finally got it. The result validated one of the key conjectures made by the Grad and his team back in 1950s. And that's a big deal. Now we can move forward to complete the proof of principle of the Polywell Fusion machine. So you can read about details of experiment, and the paper should be being reviewed now, hopefully to get published soon in a scientific journal as well. So what ended up being is, in order for the Polywell to work properly, we actually need two concepts to work at the same time. We're able to do this electrostatic fusion by forming a potential well early days. And that's when you get to see a lot of neutron data. We had a very hard time dealing with this high beta cusp or WiffleBall effect, but we finally done it in 2013. That was a big step for us. What we really need to do is do two of these things. Now we have two pillars of the Polywell. We have to do both of them at the same time. That needs to be done, and that's something that we like to do it. Before we talk about more the near-term plan, I want to turn your attention to where do we go from there. And this is actually interesting. What if the Grad's estimate on how fast you lose those plasma in the cusp is valid? What if Bussard's idea of using electron beam to accelerate the ion during the WiffleBall phase of those high beta cusp works well? Say about 50% efficiency. I mean, because if you look at our numbers, we're getting 7 kilovolt type of potential wire with about 8 kilovolts beam injection. So 50% looks quite achievable. The question then becomes, can we make a net power producing Polywell Fusion machine? And what does it look like? You want to know where you want to go first, eventually. And that's the idea behind this. So we did some exercise on it. And that's the sort of the cartoon. And this one is meant to be the scientific machine. And designing a fusion reactor is very time-consuming, and I didn't quite want to do that. But what you did is, with a quick and dirty calculation, you can estimate how big this system has to be. So what we learned is about, if you have a coil size about 2 meter radius, have about 5 Tesla with about 80 kilovolt beam injection, you get about 98 atmospheric pressure, plasma pressure in your system. That's pretty.
100,000 times more than you were talking about a moment ago for the smaller machine.
I know. So just 1 second. We'll get there. So anyway, I have to know beauty of physics is, once your underlying equation is valid, there's no real limit about you can take a baby step. You can take a big step as well. But nonetheless, you do have to validate it. But what I want to do is, if this machine looks far from attractive, then what's the point? Because you have to validate it. Assuming those predictions have some validity in it, you need to know where my end game is. If my end game is interesting, I'll spend time on it. If my end game looks deeply, it's not hopeful, then we should spend our energy on something else. So that was meant to be this exercise. We get about 1.1 gigawatt of the power, assuming about 50% energy efficiency in use if you use a DT fuel, and you need about 185 megawatt to continuously heat it up. It's not an easy machine to build. I agree. I mean, however, this is not that bad. Current engineering and technology is there. If you put your resources in your mind and have your team, you can do this in a few years. Maybe not cheap. It'll probably cost a few $100 million, but you can nonetheless do this at a relatively short time frame. And I'm going to show one quick animation movie. What's also nice about Polywell is it's almost like a little cartoon. You get to see it. It's a relatively easy machine to assemble and also maintain if you want to play with it. In fact, we've done some of those during the WB, the high beta cost test system. So you can, if you need to assemble it or need to replace it, you pick it up and you just drop it and open the half the can. It's a relatively simple machine to build and maintain. It's very attractive engineering-wise. At some point, yes, I love to do science, but then I have to appeal to the bean counter. That whatever I wanted to do, there's an end game that is attractive. So thanks for the question. You're very, very correct. That's where we are. We want to be about there. So exactly 100,000 times in terms of confinement time scale. That's what we have to do. These are the parameters that the machine that I show you, these are the parameters that where we eventually need to go to make a net power machine. What we have is that we have an equation that was derived. We don't know qualitatively, Grad conjecture there is a validity in his conjecture. As soon as you form high beta, it does improve your high energy electron confinement dramatically. There's no doubt about it. The question is, how well does it really improve? Is this line correct? Are you going to be poor, so you're not going to get this, instead you get this? Clearly, in that case, you will never be able to build net fusion power machine. Can we find a way to overcome and do even better? I don't know yet. So one of the realistic things is, in the next 3 years from now, we would like to test it out, what's going on, validate this equation, understand it. And if you can generate the data points here, we're going to take about factor up here to about 100 to 1,000 jumps here, to a few milliseconds. If your equation fits in about factor of 100 or 1,000, you're starting to get comfortable. You can start extrapolating toward that. In fact, that was the approach made by the ITER design. That's what we do it in Fusion. You do check all your results. You do its best job, but sooner or later you have to make a jump. And part of the physics is it doesn't change. It's there, and you can start looking beyond that.
It's not only you want to increase the time that you keep the plasma, it's also the pressure.
Oh yeah, everything will go up. So 2 kilogauss is not a strong field.
Yeah.
You have to be about 5 Tesla.
What is the difference? I
Okay.
don't remember Gauss versus Tesla.
Kilogauss, 10 kilogauss is 1 Tesla.
10 kilogauss.
Yes. So if you look at it here, in a Polywell machine, you have equal plasma pressure and magnetic pressure. So you can kind of calculate that, because it's meant to be a beta equal 1 machine, meaning that you have using your magnetic field as best as you can.
What limits do you reach the maximum magnetic field that you can? Because the magnetic field that you use today is not very strong. I remember the magnets of this size can create.
No, actually, you can create about 12 Tesla or so field about this big size.
But you use very small.
Eventually, this is not going to be small either. So 5 Tesla is doable. It's not going to be cheap, but it's doable.
No, my question is why today you use so weak magnetic field?
That's a good point. One of the reasons is, how do I say? That we had a magnetic power supply has a certain limitation. For the system, you need enough magnetic field to make the whole plasma system magnetically interesting system. So we could do about 1, 2, 3 kilogauss. But we couldn't do much more than, say, 5 kilogauss. 2 kilogauss is where we took a lot of data. When we dropped the magnetic field, plasma seemed to overpowering it. If you increase the magnetic field, we probably have to increase our injector quite a bit. Idea was, eventually, if you have time and energy, we use more than 2. But, because you like to have a symmetry, and if you've seen some of the earlier movie, symmetry was quite poor with just 2. But fortunately, it worked with 2. We see enough strong signal. So there's really no need to add it more than 2. But real plan is making 350 megawatt. If we have 2 more, we could have gone double the power. So we could increase the magnetic field accordingly. But since we got the result with even though the symmetry was poor, we're just happy to say, well, that's good enough for now.
Basically, increasing magnetic field will change the system. You need to make it weaker so it's actually isolated.
Yes. So better the magnetic field, eventually better, but your pressure you're handling also will go. Yes. So that's sort of where we plan to be. We have pretty good idea about what we like to do in the next 3 years. This phase will be very important. We need to address these areas. We have to sustain the plasma at about 5 milliseconds. That's about a gain factor of a few hundred from where we are, but marching toward it. It's about halfway point we need to go. We'd like to demonstrate about 10 kilovolts potential, the acceleration of the ion, and also verify that his scaling is quantitatively correct. Or we need to know if it's not, we need to know how off we are. Are we off by a factor of 2, or are we off by a factor of 100? Obviously, if you're off by a factor of 100, it's not going to work as a fusion reactor. We need to know that. If it's off by a factor of 2, that's easy to make up. So that's sort of the plan we have it. We're almost there, so that's actually pretty good in time. So this is what I see it. It still have a path, but we now see a path to make fusion power work with the Polywell. Not 20, 30 years from now, but sooner than that, if it works. It'll be great to address those needs for the energy. Right now, we're using about 21 trillion kilowatt hours. That's a worldwide number. It grows about 2.2%. Over the years, by 2040, we're looking at almost 40 terawatt hours. We're spending about $150 billion a year just to build the new power plant to meet those demands and replace some of the old ones. That's what we are planning to do. If somehow fusion works and generate power economically and sustainably, you can now address the issue that maybe I don't have to use as much coal. But also, you can start thinking big and dream about it, where you want to be, use this new source of energy. One of the areas would be obviously electric car. That'll be great. Estimation is about 5 to 7 trillion terawatt hours will power about 1 billion car, mostly passenger car here, that is now being driven on the road today in the world. Maybe not in Seattle, but in California where I live, water problem is very severe. If you can address it, thanks to the technology developed using membrane, now the desalination doesn't look that far. You need about 2.6 trillion kilowatt hours, which is about 10% of currently what we use. That'll help to provide about 20% of the water needs that we are facing now. So you can start thinking about having a available, reliable source of energy that is economical and has a minimal impact to the environment. You do have a chance to change the world in a much better way. So that's what we envision it. So I'm going to summarize it. Hopefully, we visited that fusion is the ultimate energy source, but the fusion research has been and still is a very challenging endeavor. Please do work on the computer, that would be great. I do applaud you. But there are reasons to be optimistic at present, especially with all the progress in fusion research and technologies being developed during the past decades. Computers getting better, pulse power systems better, beam drivers getting better. Everywhere you look around it, it's a remarkable period of time. I mean, you can be pessimistic or you can be optimistic. I see actually exciting future lies ahead of us. And recent breakthrough in high beta Cusp will hopefully catalyze our effort to complete the validation of the Polywell Fusion concept in the next 3 years. And hopefully I'll be back here in about 3 years to give you some of the update on it. If proven, Polywell technology will offer a low-cost and rapid development path that to power the world economically and sustainably. And the reason I'm confident and I'm excited about is these are the unique advantages of the Polywell that is inherent in its design. It is inherently a stable system. Plasma stability is come from those shapes, and is one of the first stable magnetic field systems. We invented it. It is important for the economical and reliable reactor. High beta Cusp is also important because not only provide a confinement, it can make the size of reactor small because it's a high beta system. And then use of electron beam driver is kind of interesting. I was talking to John earlier. You know, it's a Farnsworth is credited as the inventor of the television, and he used electron beam to raster to make a picture. Well, back here, we're going to use electron beam to drive the fusion reaction. And turns out, among the available technology to heat the plasma to the fusion temperature, electron beam, if it works, are probably the most efficient technology we have currently. So I'm very excited about it, and thank you for your time.
Everybody made it past lunch. I see there's questions. There's a question online from Eugene, and Eugene is asking, are kinetic instabilities of any concern here? After all, we have a very hot beam electrons and relatively cold background plasma. Such distributions tend to generate kinetic instabilities, right?
That would be the case, yes. We do see the possibility of the kinetic instability being played. Generally, as we know, kinetic instability will create a more like the small-scale turbulence and loss of your confinement, but not a catastrophic. And the nice thing about Polywell is we start with a relatively compact system. We have room to make it bigger to compensate some of the leaky nature of the kinetic instability, which is not like the catastrophic. They're more of the nuisance in our view. So we are aware of it, and that's something we need to address during the next phase of the research. And I think there was a question about, could you repeat the question? There was a question about some of the scaling.
Yeah.
That's a good point.
It seems like there's a non-dimensional constant lurking in there. Like, what is it? The scaling of, there's scaling of escape cross-section for the electrons, and then a fusion cross-section, and then something with the number of ions on electrons. What's going on there, right?
Sorry, let's see. Number of ions are related to how dense your plasma in a given volume, so that's okay. Escape hole, or the loss rate of the electrons, you can kind of derive it as a diffusion process. And this is sort of the heuristic, the process. We don't know all the details about it, but we can recover Grad's result by looking at if there's a diffusion process of those electrons, and if their time between two processes about the time they cross the Cusp field, and their characteristic time is gyro radius, because that's the only scale you will have. There's no magnetic field here. All the magnetic fields are there. You can recover Grad's loss rate from the simple diffusion equation within general good agreement. So that's what we are looking at it. Clearly, there's some need to understand better. We also expect some sort of plasma flow as well there. So it's something we still don't have everything right. What we saw experimentally, which is a nice thing about being experimentalist, is you make a measurement. Do I see more electrons being piled up in the center? And that's what we saw. So we now go back and let's do some more, and let's generate the data to understand what exactly is causing the loss of electron to decrease such a significant manner. As far as cross-section, that's like when you have lots of plasma, they kind of move around it. And occasionally, fusion cross-section, they hit it. And when that hit it, you can have a fusion, but that's very unlikely event. So you have to keep them alive. In a Polywell, general number you bounce around it is about 10 million times to 100 million times. And then they'll go through one fusion collision. Please.
I don't know if you didn't mention it, so I don't know if it's still a factor, but online there was some discussion of the ions not having a Boltzmann distribution, and this being kind of a loophole in the Lawson criterion. But you've mentioned here confinement times of milliseconds or even seconds. It seems impossible that you could confine that long and not have a classical thermal distribution.
Oh yeah, in our assumption, ions are supposed to have a thermal distribution. But keep in mind that.
So you're expecting this to achieve a conventional Lawson
Yes.
criterion?
Yes.
Okay, good.
It should be sufficient enough. And that's why when they look at the Cusp, even back in 1950s, they're comfortable they can do it. And this one is an improved version of it. So yes, if we see something non-thermal effect, and that's actually the bit of a, let me take it back. Thermal versus non-thermal is a bit of a misnomer because what's happening is in the Hamiltonian, electric field, E phi term, comes directly to your energy term. So as they move along the potential well, they could have thermal distribution, but all of them will gain kinetic energy. That's not a thermal.
I did incidentally see that at your own site, so maybe your own site needs a little updating.
Which one was?
The EMCC
Oh,
documents.
okay. If you point it out, I'll fix it, definitely, yes.
Yeah, so let's say you get all the plasma physics to work and you get, sustained fusion reaction and confinement. How are you going to cool it?
Cool.
When you're producing power, you have to cool it and get the energy out to
Yes.
somewhere like a turbine.
Yes,
So
excellent
how are you gonna
point.
cool it?
Yes, we have an engineering design, a little bit more comprehensive than this. It's probably used a lot of off-the-shelf items, some of the more advanced reactor turbine drive type of system, which is probably a generation 4 nuclear fission reactor. We have some design, we know. It's kind of we extract what's great about what's available in the generation 4 nuclear fission reactor system. And that area started to be a little bit more like confidential, so I'm not to just keep it in, but we have thought about it, and that's something that we have to factor in. That's the reason that when I put that scaling on the distance, I put a disclaimer that it's meant to be just scientific. The actual reactor design will be quite different. Please.
Just to elaborate on that, so generating electricity, is that what you were just referring to, the actual generation of electricity?
Yes.
Or is that, okay, so we're not going to be using steam or stuff like that then?
We'll probably use a little bit more efficient than steam.
Okay.
There's some gas-cooled reactor type of concept is now being developed. And so those are more efficient. So we're looking at, instead of 30 to 35% thermal efficiency, we're looking at 40 to 45% thermal efficiency would be helpful, for example. There are catch there, just 1 second, is some fuel, like PB11 type of thing, which we are continuing to look at it, may have a potential for the direct energy conversion. We're not giving up on those. We're just going to look at it. For now, the path that I laid out to do one more. This path doesn't really depend on any of the fuel choices we make it. We're going to understand it. Once we have fill in more data, it'll give us a much more database to design which one we should do it. Thank you. Okay. Well, I have more questions than I. Okay, please. Go ahead.
ITER was talking about years ago about 1,200 seconds
Yes.
to get it going and keep it going that long. You're talking about 1 second. How long to realistically get to a point of continuous?
It's a matter of, to me, scientifically, all the physics of plasma physics, if you can do it 1 second, you're good to go. There's about 5 minutes to 10 minutes, so that's about 600 seconds to 1200, the 600 second type of number you need, have a thermal mass of your structure to reach equilibrium. That's really important for the engineering. So one of the directions we will decide it after this phase is over, we have to make a plan. This cost is probably $300 million, give or say 20% or something, is what we're envisioning it. If somebody think your result here is spectacularly good, why don't you spend more money to make this steady, longer pulse system? We'll figure out to do that. When I was looking at this, about a second type of device, my cost estimate with a realistic number is about $300 million.
And along with that, how much energy input are we talking to maintain it?
So that's what the number here was, I think. 185 megawatt is what I suspect.
For this size?
For this size machine.
But for a continuous system?
Turns out, making a reactor work is a whole different ballgame. That's something I learned in a crash course. As a scientist, I always assumed that's doable until I talked to the real serious reactor engineer. It was an eye-opener. I trust the judgment, and they told me, I can do it for you. But you're going to have to deal with a different set of the criteria, and I'll be happy to help when you can pay me. Hope that answers it. But that's doable. He was confident that he can do it. So, but it'll be a different system from this. I think there was a question there. I'm sorry. Well, that's a very good question. So you need actually all the neutrons you make if you want to do DT, because there's not enough tritium, so you have to breed it. So that's one big question that we need to address it, and I'm aware of it. As I say, one of my goals for next phase is it doesn't matter whichever fuel I use. I still need to do this to understand the science. And I really am not that, I am very much interested in whether this means something. And from what I know, ITER and all the conventional fusion program spend about $1.5 to $2 billion a year. They are based on their program to do DT fusion power. And there are a lot of technologies being developed to handle neutron, use it to breed it, and generate the power. I don't mind leveraging that experience with that. If you ended up choosing DT, if I can do something other than DT, yes, I'll definitely look at it. I just don't like to make a big projection. I'm happy it is. I know what equation I want to use it. And I want to learn more about fill the blank. And then I have more set of the database, I can make better prediction. So that hopefully that answers it.
Can we take one of the online questions?
Okay, please.
So Aaron asks, what part of the design drives the cost most? Is it the 5T field generation and management?
What was there? Oh, okay. Well, obviously it's the management, right? You have to know what it was. When we run the numbers, the most expensive part of the design was turbine. At the end of the day, you have to generate electricity to do back. If you want to make a gigawatt type electricity, that's not cheap. Turns out what's beautiful about Polywell is the coil system and chamber, those costs are now far smaller than your whole system cost, the balance of plant. So your economics now going to be dominated by something else. It's like the solar power. The panels are now cheap. Installation costs a lot more. So the cost of solar panels starting to be kind of slow. The drop is straight down because now it's not on the module cost. It's actually connecting it, insulating it, and balance of plant. And that's what you actually want to be. You want to be low enough in your core component, the rest of the system start being an economical factor. And then there you can start looking at comparable system or cheaper system than some of the conventional power plant.
Okay, let's take one more, take another real question, and then we'll get some more online questions.
Okay.
In your recent research, you get the ions in with a plasma gun.
Yes.
And the electrons and the ions coming together. But in your final one, you want to just have electrons for the drive power. Mm-hmm. How do the ions get in?
We probably will use either pellet or gas puffing, is my plan.
Okay, let's see. From another question from Eugene online. In the time needed for effective fusion and proposed reactor, approximately 5 milliseconds, won't ions cool down from colliding with background electrons?
Good question. Let me think about that. So this will help me to think. So.
You mind repeating that?
Yeah, go ahead.
Okay, the question was, in the time needed for effective fusion in a proposed reactor, about 5 milliseconds, won't ions cool down from colliding with background electrons?
Answers are generally not much. So when the ions get to the bottom, they're very fast. So the collision cross-section there is very small with the electron, and usually electron directs are not that bad. When they go up, when they slow down, they will collide with electrons, and they will probably gain energy from electrons because electrons are hot there and ions cold. So you probably get about more or less net cancellation throughout the time. So, and the ions and electrons say if it's 100 kilovolts, electrons are 100 kilovolt here, maybe 1 kilovolts. Ions are 1 kilovolt here, maybe 100 kilovolt there. They switch back and forth through the field. And I think net, I think they'll come out about even. But that's something we need to look at it. And it'll come actually as efficiency of how much of acceleration you can do it if you push toward a steady state system. So thank you, Amy. I think Eugene, was it Eugene? Or?
And we got another question from Bob Davidson online. You described scaling up to replace existing electrical grid supply. What about scaling down size and costs for a more distributed electrical grid?
Oh boy. Well, I was working pretty hard. I did miss the Seahawks game. I really did. It was bad because I was working on some of the slides. I don't think I have a good answer for that. It's something we should look at it continuously. One of the things is, it'll be a great problem to solve it. I would like to do it when I have more data.
Okay, good, fair enough. Then I'm sure as technology progresses, somebody will want to put it in their car and someone will find a way to make it smaller.
What would you need to see from the future experiments to make boron-proton fusion usable or doable?
Probably the single most efficient is this whole idea that you use electron beams to hit the ion. If you think about it, it's a very dramatic concept because you're using electric field as an intermediary. There's really no direct interaction. It's a collective motion of the electron create a field, which then accelerate the ion. We don't know how efficient that will be. And we've seen that about 80–90% efficiency when there's not enough plasma. But really no data point there when you have 10 to the 13 per cc, 10 to the 14 per cc of plasma. So I just do the number 50%. And somewhere in the slide it says, if I see about 30% number, that would be enough to go to the next phase. In order to make the PB11 work, you need the number somewhere around 90%, just because the PB11 is very difficult to do. So I'll keep a very keen eye on it, how well I can push the numbers. And as soon as I have a confidence that number can be up to 90% or higher, yes, we should look at the PB11 very carefully.
Bussard, you explored the use of different magnetic cusp or magnetic coil geometries like the dodecahedron. Is that something you guys are still exploring? Or?
Oh yes.
Yeah.
Yes.
What are the pros and cons of that? Would that configuration create more cusp lines and thus more linkage points, or what?
I think generally speaking, it's a complexity of your machine or building one to more of the spherical symmetry you can get out of it. And there's a version that you may even be able to do 2 or 8. There are different versions of magnetic field. So the word polyhedral means not just 6. There are more than 6. You can do many different ways, and we explored those. It's something that we like to do it probably in a computer simulation rather than building machine after machine. So we do have simulation tools that are now starting to develop, and they actually work fairly well. I think one of the archive side, we've done our particle simulation and put it up there. And it's getting to the point that I'm starting to gain some confidence that we might be able to use it probably a year or 2 from now, is my guess. By then, we should be able to sort of answer some of those questions.
I think we had a question. Do we have a question from one of the young people here in the audience? Nope.
So what was so hard?
Let's say, what is a good way to answer that?
Well,
no.
You need to go down and see the lab, though, John. I mean, every time you want to run a test shot, you got to pump the chamber down to vacuum.
No, it's actually not hard. It's not hard. It's fun. It's very exciting. I really enjoyed it. It's probably my own wisdom. I think it's probably the stumbling block. Because at the end of the day, the project moves as fast as I can be creative or smart. And oftentimes my brain doesn't move that fast. So that's probably the bottleneck. But yeah, it's a very fun work. A lot to be done. There's a safety aspect you need to be aware of it. You have to do it safe. No point of killing people or getting died. It's expensive, so you need to find a way to support yourself in the experiment. I think we spent 6 months to make sure there's no electrical noise coming back to our diagnostic, because when you put 700 megawatt and try to make a very sensitive measurement, it's really hard. Thank God we have a neighbor who's doing roof work in our experiment. They don't complain about it. If we have Microsoft working next to me, they'll probably complain all day long. So it needs some effort, but it's doable. And I'm kind of optimistic that we will get there.
Yeah, if you want to see something, the coolest thing I saw when I went down and visited was the fact that this was being done in an office park where you would drive by and you'd have no idea that somebody was trying to build fusion reactors.
Can you try not to tell other people?
Their neighbors probably still don't know.
You're not the old GA facilities.
No. We're about 2 miles cheaper end of the town.
What was it like working with Dr. Bussard?
I only worked about 6 months to a year in his last year. He was very frail. He mentioned a few things that still rings it. I think if we really want to do something useful with atomic power, fusion power, that's one. I guess he also had some vision, which is sort of we don't emphasize too much, but some of you know if you want to travel outside of the solar system, you need something like the fusion engines to do that. And his background is space physics, so he knew some of those. I guess he kind of he had a melanoma, so he knew his days were numbered. But I think it would be remarkable. And in some way, power is great. It's making money in some way. Or removes the pollution, but going out of the solar system would be really cool. And it's not corporate goal at all. But personally, that would be something I really like to see it. So yeah, he was into some of those as well. So.
Okay, let's try to wrap it up. We're getting out low on time.
I'm just curious how you get 700 megawatts even for a tiny fraction of a second. Like, what's big ass capacitors, or is it?
A big ass capacitor, tiny little ignitron. It's not even that big. And we actually, I guess, exceeding the specs, so we can't really get for the warranty service, but but we double what the ratings are. So if you flow that kind of power, you can get it. As a result, there's very little control it. I have a pretty good idea about how to do startup much better in a controlled manner. But for that time, well, I was pretty bad manager. So I had a team. I told them I want something in 3 months. And that's what they come over. It took about a year to make it work. But I was called for 3 months, and they told me, if you only have 3 months, this is all we can do. So that's what we settled down. And thank God it worked. So as I say, having a bad manager is always slow down the project. Thank you.
All right, this has been Dr. J. Young Park from EMCC. I'm John Daly. If you want to get a hold of Dr. Park, you can just send mail to johndaly@microsoft.com, and I'll connect you. I want to thank everybody here, and I want to thank MSR again, and I want to thank John Costello especially for turning me on to this. Thanks for showing up, Dr. Park, and doing such an awesome job delivering this presentation. And thank you guys for staying and watching all of it. Okay?
Thank you.